All right, now that we've derived the equations, I'm going to go through the process of solving accelerated motion problems. So we're starting with a step-by-step method. You want to start with making a well-labeled diagram of the situation, which includes a motion map. And what I'm going to go through on the next slide is going to be how you make a motion map. Second, you want to list all 5 of the kinematics variables. Then you want to identify all of your given quantities and what you were looking for, because you need to find that who cares variable. That's basically you're doing your knowns and unknowns. Then you're going to use the who cares variable to determine the best equation to solve for what you're looking for. And then you need to manipulate the equation without numbers. You have to practice this for the requested variable. Substitute your numbers and solve. And last, write your answer with units. Now you also need to probably check for reasonableness, and we'll talk about that with the example I'm going to do. All right, so the first part is doing a motion map. A motion map is just a picture that tells you what's happening in the problem. And there's a couple of types of motion maps that we really need to focus on. So if I have a car that is going at a constant velocity, what we do with this is we draw a picture showing the car at equal time intervals. If you think about a car going past at exactly the same velocity, constant, if you took mental pictures, you might see the car here to start with, and the car is moving forward. And then you take your next mental picture, say exactly 1 second later, and here's the car. It's still moving at the same velocity because the arrows represent our velocity vector. Now I take another mental picture exactly another second later, and the car is going to be exactly the same distance apart as the first two. So we have the first two, second two, the distance is still the same. My next mental picture, and there won't be any change, it's still going exactly the same velocity. So all of these velocity vectors are going to be the same size because they represent the same velocity. If I have a constant velocity, that means my acceleration is 0. Now on a motion map, the other thing I'm going to do is I'm going to determine what is my positive direction and what is my negative direction. In this problem, it may not matter as much as some of the others, but you should get in the habit of deciding which direction is positive and which direction is negative. Now, when you do problems like this, we usually do the direction the object is moving in the beginning is considered positive. And I know whenever I draw anything, I always draw it moving from the left to the right just because of reading. But I've seen many a student who draws it exactly opposite, and there's nothing wrong with that. Just make your positive direction the direction it's moving in the beginning. All right, so we could also have speeding up. So if we have a car that's speeding up, we may say that it's starting from rest. So here's my car in the beginning. And if it's not moving, there is no arrow to represent my velocity. We can just use a dot. Now, if I take a mental picture, the car may not have moved very far in my next mental picture, and it's not going to be going very fast yet. But if I take my next mental picture, the distance between my cars will have increased because the car is getting faster, and my arrow is going to get longer. My next mental picture may put the car even farther away. And so this is my motion map of something that is speeding up. As I said, the direction it's moving is positive, the opposite is negative. Now, acceleration, if it's speeding up, if velocity is positive, then acceleration must also be positive. If it's speeding up, both are in the same direction. If velocity was in the negative direction and it's speeding up, then acceleration must also be in the negative direction. All right, so let's look at slowing down. So for slowing down, we start with our car. This time our car is moving, and it's going to be moving, say, fairly quickly, so I'm starting with a longer arrow. And I'm just going to draw my next car a certain distance away. And yes, my cars are not going to be the same, but the arrow is going to be a little bit shorter. So when I take my third picture, instead of having this distance between my cars, the next one is going to be a smaller distance and a smaller arrow. Then my last car is going to be closer, and I'm going to say at this point it's stopped. My velocity will be in the positive direction, which, since it's slowing down, acceleration is in the opposite direction, so my acceleration will be negative. So that's how you draw a motion map. Now let's look at an example. We have a car that slows, so that's an important term. It's slowing down. So that tells us something about how to draw our motion map. And it slows down from a speed of 30 meters per second. So from a speed of 30 meters per second, so that's my initial velocity, to a stop. A stop means I have a final velocity that's equal to 0. And that's going to be over a distance of 200 meters. That's my displacement. And what I want to know is, what is the acceleration of the car? So let's start with that motion map. We are slowing down. And yes, over time, these do get repetitive. But I've been teaching physics for a long time. I've done a lot of these problems. And I will tell you, every time I get a new physics problem, the first thing I do is I draw a picture. Especially when we get to our more complicated multi-step problems, you need to have a picture to record your information, to really understand what's happening. You can't go straight to the math, or at least it's very difficult to go straight to the math. So there's my drawing. Now I'm going to have my 5 variables. And get used to doing them in a particular order, so it's just easier to remember them. And always do all 5 of them. Don't just go from the problem. Write down all 5 of them and then plug in the information. So in this case, we've identified our initial velocity is 30 meters per second. Our final velocity is 0. Our displacement is 200 meters. And we're looking for acceleration. So time is our who cares variable. So we need, of those 5 equations, we need the one that does not contain time. And that is the final velocity squared is equal to the initial velocity squared plus 2a delta x. So I've identified my equation, and now I need to manipulate it to solve for the unknown. So that's going to be a. So my first step is to isolate the term, which means I'm going to move my initial velocity to the other side by subtracting it. So I'm going to have final velocity squared minus the initial velocity squared equals 2a delta x. Now isolate the variable, so I'm going to divide by 2 and delta x. So my final equation is the acceleration is equal to the final velocity squared minus the initial velocity squared divided by 2 delta x. So my final velocity is 0 minus my 30 meters per second squared divided by 2 times 200 meters. And doing all of the math with that, you should get negative 2.25 meters per second squared. That is my answer. Now, when I say checking for reasonableness, we know that it is slowing to the stop. Since my velocity is in the positive direction, since it's slowing down, my acceleration should be in the negative direction, which means my answer should be negative. And it is. So I can now solve for the last part. It's asking how long did it take the car to stop? Well, now I have every single piece of information except for time. So I know this is negative 2.25 meters per second squared. And now I want to know what time is. I can use any of my equations that have time in them to solve this problem. So which am I going to use? The easiest one. Final velocity equals initial velocity plus acceleration times time. Because my final velocity is 0. So when I solve for time, it's going to be final velocity minus initial velocity divided by acceleration. That's 0. So minus 30 meters per second divided by negative 2.25 meters per second squared. And that will give me a time of 13.3 seconds. So it took 13.3 seconds to come to a stop. And remember, time is always positive. If you get a negative number for time, you made a mistake.